Alright, so today I'm gonna be explaining another important article with the title Hierarchical Graph Pooling with Structured Learning. This paper in 2019 from Alibaba. So graph neural networks with generalized deep neural networks to graph structured data have drawn considerable attention. However, existing GNN models mainly focus on designing graph convolution operations, the graph pooling operations that play an important role in learning statistical representations. Hierarchical representations are usually overlooked. So downsampling is overlooked. So we propose a novel graph pooling operator called HGP-SL, which can be integrated into various graph neural network architectures. It incorporates graph pooling and structure learning into a unified module to generate hierarchical representation of graphs. More specifically, the graph pooling operation adaptively selects a subset of nodes to form an induced subgraph for the subsequent layers. So again, it's a node selection. Adaptively selects a subset of nodes. So to preserve the integrity of graph's topological information, we further introduce a structural learning mechanism to learn to refine a refined graph structure for the pooled graph at each layer. So you see the architecture of the proposed operator combined with the graph neural network. The dashed box demonstrates the workflow of HGP-SL, which involves graph pooling and structural learning. The learned edges are represented as dashed lines in the graph. This procedure is repeated several times. Then a readout. This readout function is applied to aggregate node representations to make this fixed sized representation, which go through then MLP, and then you have your graph classification. So you know about how to update in graph convolutional networks is as simple as this. So first we do node selection. We get the top ranked node selection. And you're familiar with these things that you have some P projection, and once you get your edge, and the A is just the adjacency. So the next adjacency is probably with lower number of nodes. But here is important from now. We develop a novel structural learning layer which learns a sparse graph structure through sparse attention mechanism. For graph GI's pooled subgraphs at its kth layer, we take its structure information and hidden representations as input. Our target is to learn a refined graph structure that encodes the underlying pairwise relationship between each pair of nodes. Formally, we utilize a single layer neural network parameterized by a vector A. So the similarity score between node P and Q are calculated like this. So again, A is just the weight vector. We want to see the similarity score between the two nodes. And when we have the superscript K, it means that it is at the kth layer. So here we get the adjacency to the K's. the power of K's. It represents all of your random walks of length K. But sometimes when the graph is too large, calculation of these matrices is computationally expensive. Imagine if K is too big, for example, 100 layers. So A to the 100, imagine that. Do you really need to have 100 layers? Of course, traditional message passings, you need that because you need K layer to represent K hop distance between two nodes that are K distance away. So unfortunately, you have to do that. But you will see in future that I will present a lot of papers, 200 papers, so that you will see that you have much better approaches, some of them are inspired by graph random features, graph kernels, so you will see that. But here we are just calculating the similarity between the two nodes. So this paragraph is so important, so let's focus on that. You know, these H, they indicate the pth and qth row of matrix H to the K. Remember, H to the K. And H is a matrix because you have some number of nodes, but each one has some dimension, has dimension D, each of the nodes. So it's a matrix, you see. But here you get the pth, only the node P and node Q. So that's why it becomes a vector of dimension D. So now you can concatenate two vectors so we can see the similarity between them. So you have seen this several times, but the second term is really important, that A to the K. Even H to the K, if you remember here, here H is not to the power of K. It's just the update. It's not superscript. It is lower script, and it's just a simple graph convolution. And W is a trainable weight matrix. So there is nothing to do with higher order random walk. It cannot represent that. Then we have here HI. They are adjacence and node representation matrices. So A encodes the induced subgraph structure. For example, if it is 0, it means node V and Q are not directly connected. So we incorporate A to the K into our structural learning layer to bias the attention mechanism to give a relatively larger similarity between nodes directly connected nodes. And at the same time, try to learn the underlying pairwise relationship between disconnected nodes. So the first term is, I mixed it with another idea, so let me correct what I say. I'm saying that the first term can capture two remote nodes, P and Q, because here the last paragraph is saying what it means. We incorporate A, the second term, only as a bias the attention mechanism to give a relatively larger similarity scores, between directly connected. So we infer that the first term is for indirected nodes that are not connected to each other. So it also represents that. Then to make similarity score between easily comparable across different nodes, we should normalize them across nodes. So this is expensive because, again, denominator could be a large sum. You should sum over all nodes. But you are taking similarity score across different nodes. So here P and Q could be far away nodes. So here we have some graph, and the graph is connected to Q, and another direction is connected to P. So we normalize it, and then the softmax always has non-zero values. Then they give it to sparse max, which aims to return the Euclidean projection of input into the probability simplex. Now, for larger scale graph, it will be computationally expensive. Oh, this is what I said just 1 minute ago. To calculate these similarities between each pair of nodes during learning of structure. So if you further take graph's localization and smoothness properties into account, it is reasonable to constrain the calculation process within the node's H-hop neighborhood. So after having obtained the refined graph structure, we conduct graph convolution and pooling operations in the following layer. So we can have this update, and since the learned S satisfies sum is equal to 1, therefore we have the diagonal. They have the diagonal matrix, which degenerates to identify matrix I. Similarly, the calculation of node information score can also be simplified like this equation, which makes model very easy to implement. Then we got the readout of what we have obtained. Once we have a readout, you get all of the, because you need to have a graph level representation. So why not simply summing of all of these readout to get the graph level? Once you get the graph level representation, then it's a simple classification, simple cross entropy loss, and you can backpropagate to adjust your learnable parameters. So they have worked on enzyme is a very difficult data set. I mean, state of the art is very, very low in comparison to DND, proteins, NCI1. I don't know about NCI 109. MUTOG is also important. MUTOG data set. So they combined, for example, for enzyme, you see, started from 29, now we are in 68. But for protein, we have 84. If you compare it with kernels, you know, the proposed method is better than the kernel approach, much better than the kernel approach. Also, for different data sets, we have, if you compare with graphlets, or WL. WL, because it's very powerful, of course, so it's just 2% improvement. So what about diffpool? Diffpool, 5% here, 2% here. So it's a very normal approach. And then gpool.